Hello, and thanks for joining today's short video clip on heat pumps. This series is sponsored by the Colorado Energy Office.
Hi, I'm Robbie Schwartz with Built Tank Inc. And today we're going to talk about the refrigeration cycle, specifically with regards to heat pumps and air conditioners. And basically an air conditioner is a heat pump, but an heat pump has the ability to reverse the cycle. So it can take energy from outside to inside. The other thing about this cycle and this refrigerant cycle is that it's transporting energy. It's not actually creating energy. So it has the ability to leverage the second law of thermodynamics. The second law of thermodynamics says that energy always goes from hot to cold, or from higher concentrations to lower concentrations. And so if I'm trying to cool a house, I need to make this indoor coil cold in order for the hot air inside my house and the energy in that hot air to move from higher concentrations to lower concentrations, or from the air into the coil and then ultimately to the outside and then be thrown to the outside there. And that's what cools my house. Now, if the outside air is really hot, like in Phoenix, Arizona, where it's maybe 115, I need to make sure that this coil is hotter than the outside air. And that's where the compressor and the expansion valve come in. It's able to change the state of the refrigerant from a liquid to a gas, and then from a gas back to a liquid. And that's where the energy is able to, that's where we're able to actually get the efficiency of transferring energy from one location to the other location. So for example, if I'm trying to cool my house, then I need to make this coil really cold. How do I make the coil really cold? Well, I need to expand the refrigerant. And by expanding the refrigerant, I can make it cold. So for example, if I have compressed air inside this can here, and the temperature of that can is 65, if I expand the air by allowing it to flow out of this can and take its temperature again, it's now at 60 degrees. So I've changed it by 5 degrees by just letting air out of that can there. Same thing happens here. To make it cold out in this coil, I'm letting that refrigerant expand, lowering its temperature. The coil's cold, the air moving across the coil is warm, the energy's going from higher concentrations to lower concentrations, and then it's going to the outside. But when it gets outside, I need to make sure that this coil is hotter than the outside air. So I'm going to compress that refrigerant. And by compressing the refrigerant, just like I'm going to compress the air inside of this plunger here, I'm going to raise its temperature. So the temperature of the air inside this plunger is now at 71. So I'm going to plunge this down here, and I'm going to increase its temperature. Now it's at 73, it's at 74 degrees now. And that's a small example. These systems are able to really exaggerate the temperatures there in order to transfer the energy from one location to the other location. So I've taken energy from inside my house to outside the house. Now, the thing that's really difficult for us to understand is that there's a lot of energy in really cold air. So if it's negative 10 outside, I need to make sure that the coil temperature is colder than that outside temperature. So if it's negative 10 outside, I need my coil to be at maybe negative 20 or more. So if I reverse this situation here, I send it through the expansion valve and I cool that refrigerant more than negative 10, the energy outside in that air that's in really cold air, but there's energy there, is going to move from higher concentrations to lower concentrations. In essence, from hot to cold, because it's negative 10 is hotter than negative 20 there. And then I'm going to bring it inside and I'm going to compress it, and I'm going to exaggerate that energy flow, and I'm going to take it through a coil, and it's going to be hotter than the air moving across that coil, and I'm able to move that energy inside the house if I have a heat exchanger system. I can also just dump it inside the house if I don't have a type of heat exchanger system on the inside there. So that's really the simple way that the system works. It's leveraging the magic of refrigerant, the magic of being able to compress it to increase the temperature of it, and able to let it expand to decrease the temperature of it, and then be able to use the second law of thermodynamics, that energy moves from higher concentration to lower concentrations. We can think of it from hot to cold there. And that's how we get the magic of this system working. And so next we're going to talk a little bit about the different types of heat pump systems that are out there that we might be able to take advantage of.
Hi, I'm Robbie Schwarz, and now I'm here with Sean Lamons with Mitsubishi Heating and Cooling. Thanks so much for joining us today.
It's good to see you. Thanks for the invitation.
So today we're going to talk with Sean about the application, how you actually put a heat pump and match it to the house, and what type of different heat pumps there are that are available for you to choose from. So Sean, let's start with kind of how do we match a heat pump to the house?
Yeah, so matching a heat pump to a house really starts off with thinking about the different capabilities of the heat pump, right? And so starting decades ago, probably approaching 40 years ago, there were heat pumps available in the US, and they were we'll call them standard heat pumps, and they didn't go down to low temperatures very well. So you would start to see tapering off at 40 degrees, 30 degrees, and so on. And so it set the pace for a lot of HVAC contractors that were not comfortable with how heat pumps worked, right? Because they weren't delivering comfort at those lower temperatures. Now with newer technology, within the past 10 years, 12 years or so, you're seeing heat pumps that are capable of going down to not only 0 degrees, but negative teens and even beyond, depending on the capabilities in the system you choose. So we're looking at a cold climate heat pump that can handle the temperatures in Colorado that we see. And we're looking at standard heat pumps that are still a decent match up for a house that already has, say, a heating system, and they just want to switch away from some of the fossil fuels, right? They want to replace an air conditioning system and still have some heating capability at moderate temperatures.
Okay, so we talked a little bit earlier in this video about being able to take energy out of really cold air, and because Colorado is a relatively cold climate in the wintertime, you're talking about these cold climate heat pumps' ability to do that in a more efficient way?
Yeah, they're more efficient because at the heart of the system really is a refrigerant, right? And that refrigerant, it's a bit of a misnomer for a heat pump, but it allows for that phase change to happen. That's really where the magic is in a heat pump, right? Where it's kind of like a pulley or a lever where you're applying 1 unit of energy in and you're getting multiple units of energy out. And that's where it's the phase change, it's the compressing of that cycle, that refrigerant cycle.
Great. Okay, so if we're talking about installing a heat pump in an existing home versus a new home, do we need to think about other energy efficiency issues with the house?
Yeah,
before we actually put the heat pump in?
Yeah, exactly. You were talking about matching the heat pump to the house, and the envelope really sets the pace for the heat pump and the systems that go into it. So it depends on the insulation, the R value in the ceiling, the walls, the windows, the floors, etc. That envelope sets that pace, and now we can calculate how much heat needs to be done at various temperatures. Now that heat load calculation can then be looked at with the heat pump that there's different heat pumps that are out there. We're looking for the right matchup. And once those are properly matched up, now you can do not only 40 or 50% of your heating, you can do 100% of your heating at the temperatures we see in Colorado.
Great. So I think that explains that really well. So let's move on to the different types of heat pumps that are available. We're standing in front of one specific type. Why don't you tell me about this and the other types of heat pumps that people can choose from?
Yeah, so this is a 2-fan, 2.5 ton heat pump. It's a cold climate heat pump. And with the improvements that I've done on my house, so I had some insulation added, I had air sealing done, I had improved the windows. Those are pretty common things for a lot of efficiency-minded folks. And I've dropped my heat load down, so I was able to step away from my 80,000 BTU furnace and just use this cold climate heat pump. It's got some southern exposure, which is a great spot for it. That helps manage a little bit of snow and ice. And it's not that the system can't handle snow and ice, it's just that we're going to give it an extra boost in capability, and it's going to be even more efficient that way. right? It doesn't have to defrost
Yeah.
as much and that kind of thing.
Okay, so you've hooked this system up. So this is the actual heat pump that extracts or brings energy from outside into the refrigerant, ultimately to the inside. But
Right.
you're distributing that heat and cool energy through a duct system. So can you tell me that kind of difference between ducted and unducted systems?
Yeah, so what's this connected to and the
Yeah.
options there? Yeah, so not only is it air conditioning in the summer, it's heating in the winter. For me, it's connected to a central air handler. I have a regular furnace inside that runs that fan during the winter and the summer to distribute heating and cooling. That's a ducted system. There are other ducted system options as well, depending on what's a good fit for your house. There are also, when most people think about heat pumps or mini splits, they're thinking about that thing on the wall,
Yeah.
right? And that is one of many options as well. Maybe it's a good, cost-effective option. It is really the most efficient distribution option that we have. But you can do a ceiling cassette as well. It's a little bit easier aesthetically, and the good news is there's lots of ways to get there. The bad news is there's lots of ways to get there.
Yeah.
And that kind of makes some contractors leery of, now I have to design around more options, right? So it does add a little bit of complexity, but with the right approach and the right design ideas, you can really get something not only that is more efficient and fits the need of the house, but you can have zones in the house and you can have individual comfort around that existing home or even a new home. And it really adds a whole new livability to the house.
Yeah. So it sounds like it kind of is boiled. If we boiled it down, it would be a couple things. One, we're looking for either a ducted or unducted heat pump. Then we're looking at what type of efficiency the base house has and how we match the heat pump to the house. And then are there other good resources that people can look to find out more information about heat pumps?
Yeah, so the Colorado Energy Office has some great resources, and I believe they've partnered with another website called Love Electric, and there's some great resources there as well. Local utility companies, check in with them. Colorado Energy Office has been very active in partnering with lots of groups and organizations and individuals around the state to promote the development of the heat pump market, because the technology is there. People are starting to understand it. There's more and more contractors every day that are trained in it. It takes a little bit of patience, but what changes don't take a little patience, right?
Yeah. So it's loveelectric.org, correct?
Loveelectric.org, exactly.
Great. And there are a variety of different manufacturers that manufacture heat pumps, right?
Absolutely. Yeah, there's some great manufacturers out there. Stick with a top tier manufacturer that has a good reputation, has been around for a while.
Great. Well, thanks so much for your time. I really appreciate it.
Good to see you.
And I think we did a good job explaining that.
Hopefully. Take care.
Thanks for listening. The Colorado Energy Office has many other trainings and resources available to you. Please visit the Code Adoption Toolkit in the link below.